Okay, now that we have gone through and did our pre-lab for the amount of hypochlorite in bleach, that you've actually watched the lab or performed the lab yourself in class, it's now time to walk through that amount of hypochlorite in bleach. I want to walk through first some of the data. I want to then walk through the calculations. Then after I do that, I want to walk through a separate set of sample calculations. So I'm not going to do the calculations for the numbers you see here or any one specific trial. I thought it would be best to just use a set of sample data, show you how the sample data was used, and then hopefully you can apply that to the data we have here. So anyways, we'll start with the reactions. You'll see the first reaction was the reaction that occurred in the volumetric flask. We took the 25 milliliters of the bleach solution. That was the diluted bleach solution. That's the ClO minus. To it, we added the 2 grams of potassium iodide. That's the I minus. And then to that, we added 2 milliliters of hydrochloric acid, so that acidifies the solution. Therefore, inside of the flask itself, we have chloride, iodine, and water, and then it would be there would be excess of the iodide, and so that's the second reaction. You'll see the iodine plus the excess iodide forms the triiodide ion. The triiodide ion is what we are titrating with the thiosulfate that was in it was about 0.1 molar, pretty close to that. I have the concentration down here. That is what was in the burette. So what we do is we titrate it. As we're titrating the thiosulfate into the triiodide, that deep, dark, reddish brown solution becomes lighter and lighter until at one point it becomes a light yellow solution. When it becomes light yellow, we then added a full pipette of starch and it becomes a dark blue. It almost looks black, but it's actually a dark blue. That's called the starch triiodide complex. And so then we continue to add the thiosulfate until all of the triiodide is reacted. We call that the equivalence point, where the moles of triiodide are completely neutralized by 2 moles of the thiosulfate. At that point, since there is no triiodide left, then the reaction is over, and it will go from that blue-black color to a clear and colorless solution. So those are our 3 reactions. So when it talks about the reaction section, went over these in the pre-lab, but they are here as well. This is the data from the lab itself. I uploaded this data table. Hopefully everything has had some issues with it at first. So if you saw it earlier, you'll see that I did do some modifications to it. Noticed some things that were omitted and a slight error in the concentration. So now I should have this all kind of worked out. At least it looks like it. So we have our initial volume. So the people who are watching this, those of you in GATE that saw me do this lab, these are the things that you would have seen me add to this. And so we started first at 0.00. That was the initial volume of the burette. And then the final volume of the burette is 22.49. I then picked it up from the 22.49 in trial 2, went to 45.61. And then from there, I went down to the last one there, which was, I had to start all over again because obviously I didn't have enough to do another titration. And so I went from 0 to 22.98. From all of this, we should be able to calculate the volume titrated. So that's very simple, the final minus initial. I did put the uncertainties here of the burette. You'll see that. We'll have the volume titrated. I didn't put any units or any plus minuses because that's going to come from your calculation. And then we'll find the average of the 3 volumes titrated. Everything that we do for the percentage will be from that average. Now, the deviation from the average, this is actually precision. When we talk about the percent of hypochlorite in bleach, that's a percent error. When we talk about deviation, deviation is a precision. So the deviation would be the agreement of your trials with one another. So when we say you are being precise, we're talking about how close is your data to itself? So were you able to duplicate your results well? That's what the deviation from the average is. And so you'll see that deviation from the average. And I'll show you again these with the data that I have. Then you have your average deviation. Those are again in milliliters. There's no plus minus with these. We go down from there and then we get our relative deviation. Again, that's just gives us a deviation relative to the average itself. Okay, went on from there. I have the concentration of the bleach, of the sodium thiosulfate. You'll see it's that there. I don't show this in the video, so I wanted to make sure that you had that, and it is up online in the actual data table itself. So you can see that, and I went through and I used the data from what I actually made so that you could see from what I did what the total should have been for the concentration of that bleach. Okay, let's see what else is here. Okay, concentration of the diluted bleach. And you'll notice I highlighted all of these. The reason I highlighted them is because those are all calculations. The bleach that you used was 7.50%. Take note that the bleach that I'm going to show you through a calculation, that is actually 5.25%. And I'll mention that. It's a different bleach sample. I used data from a different year, different example, but yours is 7.50, and then your percent error and relative error. So we have our data table, and then we move down to the calculations. First thing we start with is the volume titrated. That's the first thing that I highlighted. Volume titrated, final minus initial. That's nice and simple. This will have a plus minus value, as you're going to see. The average volume titrated, probably one of the more complicated plus minus values, because with this one, you're going to have to do two different errors associated with it. You're going to have to do a plus minus for the addition and then a plus minus for the division. Deviation from the average, you'll notice an absolute value here. Deviation is just how far you are from the average. It's not a positive or a negative. So whether you are above it or below it, it's just how far did you deviate from the average. Again, a value that is going to tell us our precision. And you'll see I put in there where you get that average volume titrated. You'll notice that deviation that you get comes from number 3. And then I'll put that over the average times 100, and that comes to my relative deviation. Now, if you come up here, you'll see that the relative deviation, I should probably make this a little bit more clear because that's really not true. We're going to do the average deviation. There's only one of these. We're not going to do a relative deviation for each trial. We're going to do a deviation for all of our trials. Okay? So our average deviation all over the average volume titrated will give me my relative deviation. No plus minus with this. It's just a percentage. Concentration of the dilute bleach. We're going to take the molarity times volume, M times V. And so we're going to take that average volume titrated in liters, all multiplied by the concentration of the Na2S2O3. Now, this is where it gets a little tricky. You'll see it says 2 to 1. Now, here's why I say that. For your thiosulfate, once I get the moles of them, there are 2 moles of thiosulfate for every 1 mole of triiodide. That's the first ratio. Then I trace that back to the second ratio. There's 1 mole of triiodide for every 1 mole of iodine. That connects me to the first reaction, where 1 mole of iodine for every 1 mole of hypochlorite. And so it's like a transitive property. If there's 2 for every 1 iodide, and every 1 iodide for every 1 iodine, and every 1 iodine for every 1 hypochlorite, then I can just eliminate all those middle steps just to kind of shorten up my work, to say there's 2 moles of thiosulfate needed for every 1 mole of hypochlorite that I started with. Once I get those moles, I divide it by the 25 milliliters that I started with in my Erlenmeyer flask, and so that will give me the molarity of the bleach in the Erlenmeyer flask. But remember, that bleach came from a 5 milliliter pipette out of the bottle itself, and so I used MV equals MV. Now notice in here I gave the uncertainties associated with your pipettes. So here we have our 5 milliliter pipette is a 0.01 uncertainty. Our 100 milliliter volumetric flask is a 0.08 milliliter uncertainty. And then I showed you we're solving for the concentrated bleach. So here is I start with my X value, then the 5, and that equals the molarity of the diluted bleach, what I got from number 5, times 100 plus or minus 0.08. Once I do that, I will know the concentration of sodium hypochlorite in the bottle of Clorox bleach. I then took that and I took the molarity, so that's moles per liter. 1 liter is 1,000 milliliters. 1 milliliter is 1.08 grams. So what does that give me? That gives me the grams of solution. That 1.08 is the density of the bleach. Then I took the grams again of the NaClO. See, 1 mole of NaClO for every 74.5 grams, that's the molar mass. And essentially what you would have solved for is the grams of hypochlorite per grams of solution. When you multiply that by 100, it gives you a percentage. That percentage I will compare to the 7. Oops, let me make sure I got the number right. It says 7.25. That's not right. Hold on, let me correct that for you very quickly. It's actually 7.5. I was thinking about the example I gave you. This is 7.50. Sorry about that. Not 7.25. Okay, 7.50. So you take your number minus 7.5. Remember, that'll give you your percentage or your data to determine the significant digits. All over 7.5 times 100. Notice again, this is a different value of precision. So there is the precision in your results. This is I said precision, I meant accuracy. This is the accuracy, and so this does not have a plus minus. And so then we do have our precision in the equipment, and that is our absolute error over the relative error. For the lab report. So this is a lab notebook report, one of those ones like we've talked about before. When you have a lab notebook report, in a lab notebook report, there are a couple of things that show up there. First thing is you have a title, and so we'll give a title of the lab with your name, obviously, and the purpose. So what was the purpose of the lab? Right? Obviously, the purpose of this lab is to determine the amount of sodium hypochlorite in bleach. You'll then list the equipment that is used, and again, if you look at the lab, you'll see a lot of that equipment that's there. So what was the equipment that was needed? And then we go into the procedure. So remember, this is a procedure written so that somebody could follow. And so if I picked up your lab, and again, this is normally what we would turn in a lab notebook, but since, obviously we're at home, that's going to change. We're going to probably type or write these up. So if I were doing this procedure, I'm going to write, the first step is to pipette 5 milliliters of bleach into a 100 milliliter volumetric flask and dilute to the mark and mix. So those are the kind of things that I would have said in step 1. And then I would talk about pipetting 25 milliliters of the diluted bleach into a 250 milliliter Erlenmeyer flask, add 2 grams of solid potassium iodide and 2 milliliters of 3 molar HCl, and swirl the solution. So what I'm doing is I'm giving you essentially a summary of what was done, but also something that I could actually follow. So if you give me a summary that's something that requires me to look back at the lab, then you're not giving me an effective summary. And so you got to remember that when we're doing this, the actual summaries need to be something that a person could pick up and follow and perform the lab themselves. Okay. Also, don't forget to tell me where this procedure comes from. Every lab comes from the same place, laboratory experiments for AP chemistry, right? So after our procedure, the next one, you're going to give me the reactions, and there are 3 of them. Remember, these are net ionic equations, so please do not forget all of those charges. Okay. We go on from there. The next one is the data. We saw the data table. And so you can see the data table that needs to be included. I have all of that there with those 3 trials. Finally, we have our calculations. So you'll be sure to show all of your calculations. The good news is we're really not looking at each trial. What we're looking at is an average for most of our calculations, as again, you'll see in my example. Error analysis. What are 3 errors that you could have made, and how could those errors affect the lab? How could they be minimized? So you have to think about these. Do you have high results? Do you have low results? And how could you get those results? And a lot of this will come back to the fact of your titration. And so one of the keys to this that I should have addressed in our pre-lab is a lot of this goes back to the titration. Did you add too much or not enough of the sodium thiosulfate? Well, the amount of thiosulfate will determine your amount of bleach, because if your percent of bleach is very, very high, then you will need more thiosulfate, because you're going to need more thiosulfate to to react at all. So high results would generally be things from an over titration. So more of the liquid came out. You passed the equivalence point. You had a drop on the side that didn't reach the inside. That you didn't fill the tip of the burette. That you had. Let me see. What's another one? I'm trying to think of another one here. That if, so did I say a drop on the end? If you didn't coat the inside of the burette. Those are all high results, meaning I got a number for the percent of bleach that was bigger than 7.5. If it's less than 7.5, well, a lot of times people will say, well, you under titrated. Well, here's my question. Did it change colors? If it changed colors, you can't under titrate. So that can't happen. So now you got to look to other things. You got to look to your bleach itself, because was the bleach itself, number one, was it old? I don't know when I bought it. I mean, I know when I bought it, but I don't know how long it sat. Bleach degrades over time. And so as bleach breaks down over time, the bottle may say 7.5, but it may really be 6.75 or something like that. When I was making the bleach solution, did I actually get 25 milliliters from the pipette? Did the level go somewhere below that line? Did I go past the watermark on my volumetric pipette? Did I coat my bleach pipettes? Those are all things we consider, because if you got something less than 7.5, that means that you didn't add enough thiosulfate, and there is no possibility of under titration. And you say, yes, there is. No, there isn't. If it changed colors, you either hit the equivalence point or went past, because if you don't reach the equivalence point, the color will not change. It wouldn't have gone from that dark black. Now, if you said it was still the color and it didn't go away, well, then that's a different story. Okay. Well, let's then go down the last part, conclusion. So what is in the conclusion? Purpose. So what was the purpose of the lab? It's a quick summary of the procedure, and we mean a quick summary. So in this case, you're talking about 5 milliliters of a bleach solution were diluted to 100 milliliters in a volumetric flask. 25 milliliters of the solution was pipetted into an Erlenmeyer flask. 2 grams of potassium iodide and 2 milliliters of hydrochloric acid were added. The solution was titrated with sodium thiosulfate until it turned from red to light yellow. A dropper of starch was added. The titration was complete when it went from dark blue to colorless. Those are the kind of things that we are looking for a summary, where it just doesn't give the whole thing. It just talks about what you did in about 2 sentences or so. Okay, again, I'm looking at the procedure part to actually do the lab from what you gave. Then give me what you got. What's the actual, the 7.5%. What was the average percent of sodium hypochlorite in bleach? Make sure to mention this was Clorox bleach, so we're mentioning the brand itself. Also, tell me what was your percent error and what was your relative error. Also, don't forget we had to compare that percent error to relative error. Remember, if your percent error is greater than relative error, that means that the errors in this lab were from you, so they were procedural or random errors. If the percent error was less than the relative error, that means that they were built into the equipment or systematic errors. Let's see. Don't forget to also tell me the relative deviation. Remember, that tells you the precision in your trials. So how good at you were you at doing the lab? There was a 1% relative deviation, which means that the lab was replicated fairly well. And you look at it, you really should have anywhere between less than a 10%, I would say probably less than a 5% relative deviation. I would think that would make the most sense to me. Anything less than 5%, and you replicated the lab very, very well. And then finally, 2 modifications to the lab. If you had to do this again, how would you do it? What would you do differently? And don't just say, if I were to do this again, I'd use better equipment. Well, like what? So tell me, would you use electronic pipettes, which measure the volumes more precisely? Would you use more trials? Would you use a higher concentration so you didn't have to dilute it of the sodium thiosulfate. I don't know. You tell me. So that's what that part is for. 2 modifications. So give me those 2 modifications to the lab. Now the final part, let's go through and do some sample data. So here is some sample data. Not exactly what you saw, but it's close enough that you could get the idea. So what I did here is I had an initial volume and a final volume for 3 trials. Notice they all start with the same uncertainty of a burette. To find the volume titrated, now remember when you're doing this in your calculations, you're going to show me number 1, the word equation, and then number 2, you're going to show me the actual numbers. I'm just showing you the numbers. You'll just plug in your data and then work from there. So I took the final minus initial volume. I got the 18.44. Now, every one of these is an uncertainty of addition, so it's 0.05 squared plus 0.05 squared, and then the square root of that. And so since they're all the same, they're all plus or minus 0.07. So I got by taking final minus initial, by doing my uncertainty calculation, I was able to find my volume titrated for the 3 trials. To find my average volume titrated, I took each of the 3 trials and I added them together. So that's where the 55.08 comes from. That's 18.44, 18.22, and 18.42. However, in an addition, you must take the 0.07 squared 3 times, add them up, and take the square root. And that came to be 0.1. So that's what's over here, is that I now took that 55.08 plus or minus 0.1. And so I made sure that they were in agreement with the uncertainty. I divided that by 3. Now, when you divide by 3, now it's not just an addition and subtraction, but a multiplication and division problem. So I went through and I took my average, which was 55.1 divided by 3. I got 18.37. And then the square root of 0.1, that was the addition value, the uncertainty with it, over 55.1 squared. So I squared the square root, and I got 0.03. And so my average volume titrated came out to be 18.37 plus or minus 0.03 milliliters. To find my deviation from the average, I just took my calculated value, so my volume titrated, and then I subtracted that from from the average of the trials. Even though some of these may be negative, you'll know that I took the absolute value, so they're all positive. So each one of these, notice no plus minus values with these. This is a precision. And so I got the number, or how far I was from the average, how far I deviated from the average. Okay, 0.07, 0.15, and 0.05. From that, I found my average deviation. So I added all 3 and divided by 3, and I got 0.09. I then took that, and to find my relative deviation, I took my average deviation all over the mean times 100. And so in this case, I deviated by 0.5%, which is excellent. So that shows a very, very precise application, meaning that I replicated the trials very well. Again, remember, 5% or less is considered excellent. Then I went to find my concentration. So to do that, I took the average volume titrated, I divided by 1,000, to put it into liters. So again, remember, this is the average volume titrated. I then multiplied that by the concentration of the hypochlorite and bleach. And I just used yours because I thought it would be better so that you could see it. And so I have it all in there. And then I used that mole to mole ratio, the stoichiometric ratio of 2:1. And from that, I went through and I showed you if I have my 0.03 over 18.37, that's my volume titrated, the average squared, plus the uncertainty over the value for the concentration. I square rooted that, multiplied it by the number of moles, and I got my uncertainty. And so the number you're seeing up here, the 0.000918 plus or minus point all those zeros and a 2, this is my moles of ClO minus. Now, if molarity is moles per liter, I took my moles all over the 25 milliliters and I converted that to liters. In order to find my uncertainty, I took my moles, the uncertain value, the absolute error, over the measurement, the number of moles squared, plus the 25 milliliters and its uncertainty. So the uncertainty in the 25, 0.03 over 25 squared, took the square root, multiplied that by molarity over volume, and I got 0.00009. I brought that back up, and this became my concentration of the diluted bleach. That would be the bleach in my 100 milliliter volumetric pipette. I'm sorry, volumetric flask. Well, what was the concentration of NaClO in bleach? M1V1 equals M2V2. So again, I took my X, which was what I'm solving for, 5, which was what I pipetted, plus or minus 0.01. The 0.0372, that's what came back from the diluted value, and then 100 plus or minus 0.08. Again, remember, the only one that's changing is what you saw in the 0.03672. When I did that, I got 0.734. To find my uncertainty, I took the 0.01 over 5 squared, that's the 5 milliliter pipette, the 0.08 over 100 squared, that's the 100 milliliter volumetric flask, and the 0.00009 over 0.03672 squared, that is my diluted solution. Square root of that, multiplied them by the 0.734, the concentrated bleach, and I got 0.002. And so now I have the concentration of the NaClO in the Clorox bleach. Now the percentage. I took the concentration, the moles per liter. 1,000 milliliters a liter, 1.08 grams of solution is a milliliter of solution. So when you look at this, the moles cancel, the liters cancel, and the milliliters cancel, so I have grams of solution in the denominator. 1 mole of NaClO is 74.5 grams. The moles cancel, so now I have my grams of bleach, or NaClO, sodium hypochlorite, per gram of bleach solution. Multiply that by 100. So when I go down to do this, the 0.002 over 0.734 squared in the square root times the 5.06, it gave me 0.01. This became my percent of bleach. And again, remember, we're only doing this for the average. To find the percent error, remember my solution that I used, this is from a few years ago, was 5.25. Yours will just be 7.5. So I took 5.6 minus 5.25 all over 5.25. When I subtracted the first two, I got negative 0.019. So that's only 2 sig figs. All over 5.25 times 100, negative 3.6%. In the relative error, again, I used the percent of bleach. I got the 0.01. This comes from, if you look back up to that 5.06, 0.01 over 5.06 times 100, 1 sig fig, 0.2%. And I think that's it. Okay. I hope that helps. Again, I didn't put everything in here because I figured that you could go back and look at the calculations to determine where your numbers fit in. But I also wanted to show you that tricky plus minus. Those are always difficult. So we've now done the pre-lab, we've done the lab, we've done the discussion of the lab, and all you have to do is the calculations in the lab report. If you have questions, let me know. Determination of the amount of hypochlorite in Clorox bleach.